I'm going to talk about our investigation of edge servers, and especially about attacks on trusted platform models. So the whole story started when our client came and asked us, look guys, we are deploying thousands of edge servers, so we're delivering them physically to some places all over the globe. Could you please check the hardware security of them? Because edge servers, they are located in different hostile environments, and usually hackers can get access to them. So the main question that he asked was, like, can you extract data from the servers? Can you modify maybe the servers? Or even better, can you turn the server against an operator or a client? So this initial question brought us to the investigation about trusted platform models. And I will present you two attacks. The first one is about sniffing, super standard, boring, nothing interesting. But second one is side channel attack against trusted platform model. It's something new, because usually we believe that trusted platform model is something we trust. So we trust our keys there, and they cannot be extracted. It turned out it's not the case. So along this journey, we also discovered other vulnerabilities related to software, but they are not going to be presented in this talk. And the work was done by several people. So me, I'm let's say founder of USEC. Roban did a big part of side channel analysis, and Karim, he helped us in research topic about software. So he consulted us and helped us in consultancy. We are all based in Switzerland. Please don't check when you send parcels, not to Swaziland, but to Switzerland, because once I got parcel sent to Swaziland instead of Switzerland. So now, what make a server to be edge or to be a central server? Well, basically, when we speak about servers, we think about, let's say, central servers, something like this. We have a data facility protected by professional security companies, serviced by professional IT people, very nicely racked. So this is a central data center, central server. But when we speak about edge servers usually located close to data generation or data consumption. It means they are delivered to the point, to the client. It can be even located in your traffic light, near the traffic light. So it's really something relatively it's smaller, but usually it's more racked, more robust in terms of hardware. And the main problem is that an attacker can easily get access to this kind of servers, because central servers, they again protected by different layers of physical security. And this kind of servers, usually even a client can be considered as an attacker. That's why I'm here, because we speak about hardware security, and hardware security of an edge server turned out to be a very challenging topic. How it looks like, so we had different models. I think we had 5 different models of edge servers. Well, it's actually a standard computer, guys. Edge servers, there is nothing special. It's maybe something between standard computer and a normal server. So edge server has a CPU, it has RAM, PCI cards, hard drives, maybe a redundant power supply, but that's the only thing. What else it has? It's Intelligent Platform Management Interface, IPMI. So it's a separate chip, separate memory, which reads different parameters on the system and controls different hardware, let's say, blocks on the PCB. But ultimately, it's just a computer with a RAM and a CPU. And these edge servers, they run an operating system called EVOS. EVOS, it's an open source operating system, Linux-based. It's developed by Linux Foundation. It's designed, let's say, around edge-specific principle and security principles. So we install EVOS on any hardware which runs Intel, AMD, and ARM controllers. And it provides us capabilities to run. It's kind of a hypervisor. So we run applications in containers, applications isolated. We can run also virtual machines. And the beauty of this setup is that the only operator, the only access who has, let's say, access to the server, it's a remote controller. Basically, if I come to the server, to the edge server, and I try to log in, I will not be able because there is no local login interface. It's only remote operator who can access, push applications, monitor what's going on the server, and this remote controller, it's managed by a different, let's say, team, different role. So you have a remote operator, you have a client, and the edge server is located on the client side. Again, since we speak about physical access to the server, EVOS enforces security. So there is a bunch of mechanisms, more software mechanisms, like read-only partitions, no SSH, no local control access, no local accounts, USB are disabled, so even if you plug a keyboard, you will not be able to use it because it's disabled. I call this software isolation, more or less, so different mechanism. But a very big part of security is related to trusted platform models. So trusted platform models is used to encrypt certain partition called vault, so it keeps a key. Trusted platform model is used to measure the booting process. I will explain a bit more what it means. And trusted platform model keeps secret key inside. And these keys are used by a remote orchestrator. Well, very basic schematic. A lot of hardware security is related to trusted platform model. So during the booting process, edge server gives a lot of information to TPM, and this information must be the same as it was at the very beginning, the same when it was provisioned. It's called measured boot. Once measured boot is achieved, so all the PCRs are correct, trusted platform model releases a vault key to decrypt partition for applications and data. And to communicate with an edge server, remote controller uses certain secrets stored inside the trusted platform model. So what I'm trying to say, basically, that EVOS and this particular edge system use TPM a lot. To make it happen, first, well, we actually consider life cycle of edge server in two different phases. The first phase is provisioning. So in secure environment, on an operator side, we install EVOS. Everything is under control, no problem, no hackers. And during this phase, keys are generated, system is measured, and everything is guaranteed as it is. And then server is being delivered to the client, to a client. So in this case, we deactivate all local accounts. Any communication is performed only with remote orchestrator. And now, every time the server boots, it must check that nothing inside was changed. And this is done with platform configuration registers. Also, any kind of tamper or recovery, let's say tamper event must be detected and reported to the operator. And even we speak about trusted platform models, now coming closer to the trusted platform model and attacks, I told you it's going to be boring. There are 5 companies working in this domain. So TPMs nowadays are using they use SPI protocol. There are 5 companies: Infineon, Nuvoton, ST, Microchip, Nations. This is a very tight market, small market, because you need to follow a certain standard called Trusted Computer Group certification. And you must pass 2 certificates, FIPS and Common Criteria. It's a security evaluation certificates, you must pass them. So market is small, entry level is very costly, so it's very difficult to enter this market. And nowadays there are only 5 companies. Probably before it was way more. And what happened is that during evaluation of one of the servers, we discovered that a trusted platform model can be simply disconnected. So we can unscrew it and disconnect, and we can even bring it with us. And before coming to this talk, I even removed a lot of slides about implants, because I thought, who is using implants nowadays? I mean, nowadays, implants are not used. Who will put implants in the server? So you won't see anything about implants here. And that's what triggered our attention, because since TPM can be removed, probably we can remove it and analyze offline. So threat model, what is exactly threat model in this case? Is that I have an access to a server. Server is not modified so far. It can boot correctly. It contains all the data, all the keys. Everything is fine. We have a budget of $2,000, 2,000 euros. It's more or less the same, but unlimited time budget. So in terms of equipment, it's 2,000 and unlimited time budget. What can we do? Let's focus first on the PCRs and the vault key. It's actually super simple. It's a very, very schematical way to show what's going on during the booting process, but the idea is that during the booting process, the TPM receives a lot of information from the system. It receives UEFI configuration, it receives SHA of hard drives, it enlists all the peripherals on the platform, and this information is given to the TPM, and TPM verifies that nothing has been changed. So during the provisioning phase, it records the state, and during the usage, it verifies that nothing has been changed. The only problem is, and once this verification is done, once everything is fine, Trusted Platform Model releases a key to decrypt persist vault, to decrypt a certain partition which contains sensitive data. The only problem with this is that the communication between Trusted Platform Model and the rest of the system is done in clear. Everything is transmitted in clear. So we open the box, basically we remove the cover, we put our sensing, our probing to the SPI interface, we record everything what's going on inside, and it gives us all the information. So we can get inputs, so everything that was measured, the output of the PCR, because they then reported to the cloud, let's say to the controller. And we also can get the vault key because it's transmitted to the CPU in clear. And that's where the part about the implant was removed, because I thought, well, theoretically you can put an implant and you can always provide the same input. So you will, like you put something inside in between this part, and you will record and you will provide all the data all the time the same. So nobody will notice that you modified anything in the system. So this attack was super simple, super standard, nothing fancy. There are many attacks like this. You can find attack against BitLocker key and maybe against other systems. Basically, you spy communication between a Trusted Platform Model and the rest of the system, and a lot of data is transmitted in clear. And then you use this data. The only problem is that we could probably tamper integrity, tamper availability of the server, confidentiality, but still the TPM contains certain unique keys. And if we want to attack these keys, they never leave TPM. They stay inside. So the only way to do it is to analyze TPM itself. There are 3 keys. All of them belong to the elliptic curves. So please don't snore. So all of them belong to the elliptic curves. And these keys are what we are targeting right now. The 2 keys are used for the ECDSA signatures, and one is used for the ECDH key exchange. So basically encrypts the traffic. That's where our evaluation started. So we acquired all 5 TPMs from all manufacturers. We designed a certain PCB to work with them. I will show you on the next slide. We actually used our platform, measurement platform presented at hardwear.io Amsterdam 2023. So if you want to see the talk, it's from there. The equipment, the total cost of the equipment, we evaluate like roughly $2,000, 2,000 francs. And the first target that we evaluated, it was Nuvoton, and that's where we found 2 critical vulnerabilities related to side channel attacks. The other 4 TPMs, honestly, guys, it takes a lot of time to investigate TPMs, so we put it in pipeline, but we don't know when we can achieve everything. So how the measurement looks like, we don't use any fancy probes. So this red board you see here, it provides stable voltage, 3.3 volt to the system. So TPM works with a single 3.3 volt power supply. And at the same time, it measures power consumption of the device, amplifies it with a set of amplifiers, and provides the output signal, the measurement power consumption, to the oscilloscope. Communication with a Trusted Platform Model is done through the SPI connection, You can use USB to SPI if you want, or we used Raspberry Pi because it was a bit easier. The entire setup looks like that. So we have an oscilloscope, relatively old, like 20 years old oscilloscope, probably even more, but it's still good. This our measurement setup, Raspberry Pico. No fancy probe, so you see really a connection, direct connection to the red board. And the only probe you see, it's a triggering. So we just generate a trigger before giving a command to a trusted platform model. This image shows you the ECDH protocol, or let's say operation. And this big power consumption here, it's a scalar to point multiplication. And that's where mathematics starts. So scalar to point multiplication is the longest and most resources and time consuming operation during elliptic curves. What it does, it simply takes a point, G, takes a point, it takes a scalar and produces the output, basically a scalar multiplied by a point. This operation involves point doubling, so this is a point doubling, and point addition. These operations are not direct, so these operations is a complex mathematical transformation involving big numbers and multiple big number operations. But both algorithms, ECDH and ECDSA, use it. ECDH algorithm use it with its own private key. So when we start ECDH protocol, we give a point to the ECDH, it's multiplying the point by its private key D and gives us the output. And ECDS, so in this case, we can control D. That's my point here. We can control D because we can, for investigation reasons, we can write our own private key. In ECDSA, we also use the same scalar to point multiplication. However, we don't control any key because it's generated randomly every time. So for investigation reasons, we cannot use ECDSA. And it turned out, so we basically took a TPM, we programmed our D, and we programmed different values of the private key. And it turned out that the duration of the scalar to point multiplication was dependent on the key length. So if we, in 2 words, the algorithm skips the leading 0 bits of the key. So if our key has leading 0 bits, it skips and removes them from the computations. So by looking in the trace, we saw that whenever we increase, let's say, the key length, we see the increase in the duration. However, when we zoom inside, it's super messy. You will see it. It's like total mess when we zoom inside. But when we increase the length, we see a step. And it means that the duration of the scalar to point multiplication gives us the key length, or it gives us the number of leading 0 bits. And there are way smarter people than me. And in 2020, they developed an attack. So using this information, basically the few bits from the ephemeral key, they show that it's sufficient to get ECDSA private key. So to make this attack happen, we need to use lattices, so we need to solve shortest vector problem. But with less than 3,000 signatures, we can get the private key. And it was sufficient for us to get 2 out of 3 keys from the TPM. So by having a relatively small information, just the duration, let's say, of the algorithm, we are capable of getting 2 out of the 3 keys used in the server. However, it was not sufficient because we still have ECDH algorithm. Scalar there is not modified. It's a constant, so we don't know much information and we cannot do the attack. That's why we had to go deeper. And here you will see what I show you. It's a scalar to point multiplication where we fix all the data we control. So we fix the private key, we fix the given point, but we still see that a lot of things are randomized inside. So when we did the first investigation, we discovered the duration of one loop iteration. And these vertical lines, dashed lines, show you approximately the duration. the place of beginning may be not correct, but this is the duration of one loop. And then when we started to look inside, we see something like similarities here, but then something changes. So basically, we could not understand what's going on. We clearly see that the process is randomized inside, even for the fixed data. That's why we came back to the beginning of the algorithm, and we figured out that at the beginning of the algorithm, the operation is constant. It's not randomized at all. So this part always the same. And when we try to match the power consumption with an algorithm, we understood that this is a point doubling, because according to the algorithm, it must happen before everything. That's how we extracted the point doubling. Then we saw this point doubling in other places. And between the 2 point doublings, we can extract the place where it was point addition. So what happens is that during one loop iteration, for some specific reason, they can swap the double or addition inside the algorithm. It's possible to do if we keep previous values, so the previous results, and we overwrite, let's say, in the new memory. So this is possible to do. It's only possible, by the way, for the Montgomery ladder. And this was already like a good step for us to understand what's going on. So we understood that this is a Montgomery ladder, double add, etc. Coming back to the trace I showed you, what was the problem is that we did not correctly identify the beginning of the loop iteration. So if we shift it a bit more, we can clearly understand the patterns, what's going on. So this shuffling, it does randomize the order of operations, but it doesn't prevent the first attack. I explained you before. So the first attack is still successful. And in our case, we discovered that there are 8 multiplications or 8 big number multiplications in doubling. And these are like these patterns, they exactly 8. There are exactly 8 number of them. And for the key additions, there are 16 multiplications, and we can see these multiplications here. So what you see here, it's a multiplication of 2 big numbers. Because to compute double or add operations, you need to apply quite complex mathematics. So the main idea of the next attack is that we would like to cause a multiplication by 0. By causing a multiplication by 0, we will change power consumption, and we will recognize it in the power consumption trace. There are 2 things you need to, let's say, grasp from this slide. The first one is that for any given point, which has coordinate x and y, the probability to have multiplication by 0 is 2 power minus n, where n is the length. So the probability in our case is 2 minus 256. So usually you don't observe this operation. This is the first point. And the second, what you need to get from this trace is that after the first loop iteration, the state of our algorithm can be considered as we took 2-bit constant, so we took 2 most significant bits of k and multiplied it by our point. After the next iteration, we can say that we took 3-bit constant, like 3 bits of the key, and multiplied by the point. So this is internal state of the algorithm. And now the idea is the following. So first we find a special point, which has 0 y. So y must be computed for every curve. Then we take 4 scalars, 0, 0, 0, 1, 1, 0, 1, 1. We find special points on the curve, which is inverse of this value that we selected, times the point, the special point, which contains a 0. And we give these 4 points to the ECDH. After 2 loops operations, after 2 cycles, we process 2 bits of the key. It means that one value from this set must be equal to the 2 bits of the key. And when it's equal, this particular operation, like scalar times the vi, will turn into 1, and we will have, as a result, a point internally which is 0 y. So the next round will use multiplication by 0. This is a bit like tricky to get, but now if you see the power consumption trace, you will see where the multiplication turns into 0. So this is a standard multiplication, and this is a multiplication by 0. You see it drops quite significantly. We can play a bit with points, we can cause multiplication by 0 in other operations, but this is ultimately the idea. So by providing a specially crafted point, we create multiplication by 0, we observe it from the trace, and we get the key. And then we do it bit by bit. So we increase let's say, our key recovery bit by bit. Again, this attack is not me who invented it. It was 2003. Smarter people always as there and present. And with this approach, we could get the last key from the TPM. So basically, we could attack ECDH and ECDSA algorithm on this particular TPM. And that's where it's actually funny, because we did this attack back in 2023. So no AI is used because in 2023 we didn't use any AI. It was discovered, immediately reported to Novaton. They corrected the results, so nowadays on the market you are not supposed to find this firmware anymore. But we can release this result only now because in between the recertification process took so long. So you need 2 years to recertify the firmware because you cannot put a new firmware on the market if you didn't certify it. So if you find a vulnerability on TPM, you need like 2 years to fix it. It's quite a long process. Because common criteria and FIPS takes a lot of time. So unfortunately, this is like that. So the advisory was released like 1 or 2 weeks ago. You can check the disclosure, the public disclosure. And that's basically it. So the lessons that we learned, first of all, when you have a trusted platform model or you have a secure element, usually it comes with a paper saying it's secure, we put a certification on it, it's common criteria or FIPS certified. Can you trust it? I don't know. You probably need independent investigation about this. It's difficult to say. So certification does not really mean security. Even if you see a label common criteria 6 plus certified, it's probably nothing. Because there are different labs and labs can give you certificate without much hassle. We spent, let's say, equipment that we spent is $2,000, 2,000 euros. So it means it's still possible to do side channel and fault attacks on secure elements using low budgets. We tried to make attack against edge servers. So we came to the attack about TPM while during attacks on the edge servers. It means that a small problem in the TPM probably can lead to more problems in your final device. So you need to consider risks. If keys are leaked or if communication is spied, there might be other mitigations you want to put in place. And the last one probably is that fixing something that is certified can take a long time. So for us, it was 2 years. And that's it. As I mentioned, I removed all the parts about implants because I thought no one using it, and that's it. Thank you.